Okay. So today we're going to study a new idea how to find the limit using derivatives. Okay. The idea is very simple. If the numerator and denominator both approach zero, then there's another way to find the derivative. Okay. So here's a simple formula, but it's hard to prove right away. And either both sides, okay, either both approach zero or both approach infinity. It's the same story. Okay. So let me roughly state the thing. Okay. So if the limit as x approaches a of x equals 0 and both, okay, or it's not infinity, this is just a, the same a could be infinity. Okay? So it's a of x equals infinity, and either both sides approaches infinity. Okay, infinity could be minus, plus, minus, plus. Doesn't matter, they have the same sign. Okay, then the limit of f of x over gx, when you're trying to find the limit, you can use the derivatives to find the limit. All you have to do is just differentiate the numerator and the denominator, as long as the right-hand side limit exists. Okay. So if the limit on the right side exists, so that's a condition. That's another condition. If the limit on the right side exists. Okay. Now, we're not going to get details to prove that. It's not true, but you can get a brief idea how to prove it. Okay, so this is we're not, majority of you are not math major students, so we're not going to waste a lot of time trying to prove it. But we understand how does it work. Okay, so here's the example. Okay, find the limit as x approaches 0, sine x of x. Now we already know that this is going to be what? Okay, we did it before. We know this is going to be 1. Do you remember that? Yeah, this is going to be 1 because by the squeeze theorem. Okay, remember we have the picture here. This is unit circle, right? And this will be x, so the arc length is x. And we draw the two triangles, and we find out sine x is less than x greater than cosine x, okay, if x is positive. So then you take the limit, you find out, oh, this is, this is not right. Okay, sine x, sorry, it's tangent x, okay, so let me repeat again. So this is a sine x, this is a tangent x, okay, the first thing in quantity, let me erase this. The first thing in quantity is going to be x is less than tangent x greater than sine x. Okay. So the height of the larger triangle is tangent x. The height of the smaller triangle is sine x. The arc length of this on the circle is x. Okay, x corresponds to the value of the angle. Okay. So from here, you will see that sine x over x is less than 1, and that's the cosine x. Okay, that's correct here. This is a unit product. Then you both sides approaches 1, and you get you get the limit, right? This is a positive, okay, when x approaches, because we're using a positive x. But when x is negative, you see that you still get same result. So this implies, this is our proof, right? Before. This implies the limit is going to be 1. Now, if you apply, yeah, for this particular problem, we have this geometry picture. We know how to do that. But some more complicated functions, you're probably not able to do this, right, in this way. So if you apply the above called L'Hopital's rule, L'Hopital's is I think a French name, L'Hopital's rule, and then you can quickly find the limit. Okay, the reason is sine x over x. This is 0 over 0 type. Why? Because both approach 0 as x approaches 0. We just cannot take the x out of the numerator to cancel x. Okay, so this is a 0 over 0 type. So we are able to, yeah, we are able to 0 over 0 type. We are able to apply the L'Hopital's rule. Okay, you have to check that first. Then the limit as x approaches 0 is going to be the limit of the quotient of the derivative. Sine x becomes cosine x, right? Derivative x is 1. So just only one single function then it's not 0 over 0. You cannot continue to differentiate the numerator and denominator. Okay, it's not a 0 over 0 type. Right now, it has a 1 over 1, right? So the limit is clearly going to cosine 0, 1, which is 1. Okay, you get the same result. So quick. Okay. Remember, we also did the following problem, trying to find the limit as x approaches 0, 1 minus cosine x over x squared. Okay. We can use trigonometric geometry to find the limit, and also using the above fact, sine x over x approaches 1, x approaches 0. Well, I can use the L'Hopital's rule to find the limit. So first of all, you should recognize this is 0 over 0 type. Why? 1 minus cosine 0 is going to be 0. When you plug 0 for x into the numerator and denominator. Yeah, clearly, right? So this is 0 over 0 type. So therefore, you can apply L'Hopital's rule. So each step when you apply L'Hopital's rule to differentiate numerator and denominator in order to find a limit, you have to check each time. Otherwise, if you got to check, you end up with a wrong result, okay? So when you differentiate negative cosine x, the derivative negative cosine x is going to be sine x, okay? And here will be 2x, the denominator will be 2x, x squared, the derivative 2x. Then, this limit is going to be 1. We already know that. Even don't need, you can continue to differentiate, right? You know, if you don't know the result, then you just, this is still 0 over 0 type. Then so it's become cosine x, that's 2, so this is going to be half of 2. Right. That's all about this idea. Right. All right. So next one. Let's try this. Find the limit as x approaches 1, x minus 1 natural log of x. Right. Now, without using L'Hopital's rule, I think it's very difficult to find the limit. Okay. This is going to be, I know, natural log of x approaches natural log of 1, which is 0, right? And x minus 1 approaches 1 minus 1 equals 0. So it's a 0 over 0 type. Yeah, this is 0 over 0 type. Therefore, we can apply L'Hopital's rule. Yeah, I don't know why this section is not put in Math 165. Okay, this is supposed to be on 165 about how to find the derivative, how to find the limit. Okay. Okay, let's try. So you can differentiate numerator, which is 1 of x. differential denominator is just 1. Then clearly, this is going to be the limit of 1 over 1, right? It's 1. So it's very clear. When x approaches 1, you just plug 1 for x into the function. It's done. Very, very quick. All right, so now we are going to look at the same problem. X approaches infinity. So watch out carefully when you apply the L'Hopital's rule. Okay. Well, go back to the L'Hopital's rule. The original statement: A here is not necessarily be a finite number. Okay. A could be infinite number. Okay. Yeah. Now to so clearly the numerator approaches infinity as x approaches infinity. X minus 1 also approaches infinity, right? So this is infinity over infinity type. Okay. Therefore, you can differentiate the numerator and the denominator, numerator and denominator, right? But this time, you will get 1 over x here, right? So when x approaches infinity, it's clearly this is going to be 0, right? The limit, 1 over x. So the answer is 0. So natural log of x grows slower, much slower than x minus 1, or any x, okay? So that's why you get this result, right? So you have to pay attention to, yeah, as long as the numerator denominator approaches, yes.
When we use L'Hopital's rule, do you want us to write LH?
Yeah, you have to mention that.
Okay.
It's better to mention that what they're doing, okay? Yeah. Yeah, you can say by LH rule, something like that. Okay, L'Hopital's. So I don't know who is L'Hopital, but you can find out. Usually, those are the people from very wealthy family and nothing to do and stay home and that totally, not like these days. All the scientists have to work for living. Early days at them. I did not do that. I just enjoy mathematics and they find something interesting and record it and publish it. Okay. All right, so let's try the next problem. All right, so this is a limit, x approaches infinity, and you can see that e to the x, yeah, you can quickly check that e to the x is good, approaches infinity, and the x squared approaches infinity. But I'm pretty sure this limit is going to be infinity. The reason is exponential function grows much faster than any polynomial. Okay, but you can see that step by step. Yeah, if the denominator is any polynomial, I can eventually prove that. Use the L'Hopital's rule, the limit is going to be infinity. Okay, so how can I do that? I can apply L'Hopital's rule at this moment. Okay, so the derivative of the numerator is still e to the x. The derivative denominator is 2x. So this is still infinite over infinite type. Okay, So when you continue to differentiate numerator denominator, put the note here. It's what type of, because that way, if you keep this habit, then you will not make a mistake. Some students just forget, keep us differentiate. And at the end, if even you cannot apply the L'Hopital, so you apply it, then you get the wrong answer. Okay. Now you get e to the x over 2. Then this is no longer infinity over infinity type because the denominator is constant. So you stop that. Then you look at, oh, what is that? The numerator approaches infinity. So this is infinity over 1 over 2. So this should be infinity. Okay, so that's the answer. Yeah, just be careful about this. Okay. Let's get some exercise from the book. Now, sometimes it's not like in quotient form. Okay, it's not in the quotient form, but you still have to, you still should try this. Okay, for example, as x approaches 0, x times sine x, sine 1 of x. Okay, we already know the limit is going to be 0. You remember that? The limit is going to be 0. Why is the limit is going to be 0? Use a squeeze theorem. Okay, use a square theorem. X sine 1 of x, absolute value x is going to be absolute value x times absolute value 1 of x, which is less than or equal to 1. I can ignore sine. Okay, but this approaches 0, right? As x approaches 0, clear. So something is bounded by another simple function which approaches 0. That forces x times sine x, the sine 1 of x approaches 0. So this implies this one approaches 0 by the squeeze theorem. Right? By the squeeze theorem. So you know this is this can be 0. Okay, here's another way to do. Okay, it's not a 0 over 0 type here, right? But I can write, yeah, so yeah, first of all, let me write down the result, okay? Using the squeeze theorem. I think this belongs to Math 165 there. Okay, I'm teaching both courses. Sometimes just confused. Okay, this is what we just studied. How to use the squeeze theorem to find the limit. Okay, so this is a problem in that section. Okay, it's 1.6, yeah. Okay, so this can be written in the form that couple ways to do. Okay, you can write it as sine 1 of x over 1 of x. Right? So you use a substitution. You can use a substitution. You let u to be, now be careful about this because when x approaches 0 from either side, then 1 of x approaches positive infinity, negative infinity, it's not very clear. Okay? So, so this becomes sine u over u. Right. If you want to use a substitution, then there's a little bit problem here because when x approaches 0, you have to say x approaches positive 0, x approaches negative 0. Okay? Then you can say u approaches infinity or negative infinity. Okay? We just focus on one side maybe. Okay? So in this case, no, you probably don't need to look at this rule here. Yeah, let me change the problem a little bit. I'm going to change it to infinity. Okay. Yeah, this one going to be limit. It's going to be 0. I'm going to change it 0 to infinity later on. Okay, let's finish this first. So when you look at this, okay, and if x approaches 0 from positive side, then it implies u approaches positive infinity. Okay, it's the same. Okay, so in this case, x sine 1 of x equals sine u over u, and that approaches, you don't know the numerator, right? But the denominator is positive infinity. So, but the numerator is bounded anyway. So it's going to be 0 and 0, getting smaller and smaller. Okay. So this approaches 0. So you can conclusion, and similarly, x approaches 0 from negative side. It's equivalent to negative infinity. U approaches negative infinity. So x, yeah, you can look at this problem in a slightly different way. This is sine u over u, and the numerator is still bounded by 1, okay? But the denominator approaches negative infinity, so but the result is still 0 because the numerator the numerator is bounded. Okay, you don't have the exact value. Sine u does not approach any number, but it's bounded, so the denominator is getting larger, larger. So you see the quotient is getting small, small. All right, so your conclusion is still, this is another way to, yeah, but I cannot use the Substitution rule here. That's conclusion 0. So if I change the problem to x approaching infinity, okay, then maybe we can apply L'Hopital's rule. Okay, this is not a 0 over 0 type, but this can be written as 1 of x and 1 of x. So what type it is? When x approaches infinity, 1 of x approaches 0. So sine 0, 0, it's a 0 over 0 type, right? Do you want to change the, you can differentiate numerator and denominator, okay? If you, yeah, you can differentiate numerator, but if you differentiate, it's very complicated. They say, if you differentiate numerator, you know, let's do this way without using substitution, okay? So this is going to be, the derivative of the numerator will be cosine 1 of x, and the derivative of 1 of x is 1 of x squared. The derivative 1 of x is negative 1 of x squared, okay? So these two cancel out. You will get cosine 1 of x. This is infinity, okay? That's infinity. But 1 of x approaches 0, so that's our cosine 0. This is the 1. Let's try a different problem. We have natural log x approaches 0 from positive side. And look at this. It's a product. Right, it is product. Right, so it's a product, then we have to change it to a quotient. So the natural way to do is x, natural of x is going to be natural of x 1 of x. Now, as x approaches 0 from positive side, what do you get? This is a positive infinity, right? Natural log of x approaches negative infinity. So it's infinity over infinity type. You can apply L'Hopital's rule, right? Yeah, natural log of x approaches negative infinity. You have to verify that first before you apply the L'Hopital's rule. Otherwise, you get a mistake. Okay. So Otherwise, you make mistakes. So now you differentiate the numerator, it's 1 of x, but the denominator is negative 1 of x squared. So you have to simplify it. 1 of x divided by 1 over x squared. The limit, after you simplify, it's going to be just negative x. It is very simple form. Okay? After you simplify it. So now the limit clearly is going to be 0. So that's the answer. Okay. You can only apply L'Hopital theorem once here. All right, so lots of even number problems on the in this section. So let's continue to do this. So we have another problem. X approaches infinite, natural log of x squared over x. So first of all, let's check the type of this this quotient. When x approaches infinity, the numerator approaches infinity. X approaches infinity, so I can apply L'Hopital rule. Right. Every time when you apply L'Hopital rule, verify the condition. Okay, you know, most of the theorem in mathematics stated like that. Under such condition, blah, 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 then you have the problem. If the condition is valid, it's not, then you cannot apply that theorem to solve the problem. Right. So you can apply the L'Hopital rule. Derivative square of natural log will be 2 natural log of x. And then you have to differentiate natural log of x, which is 1 of x. And the denominator is 1. Then you get a quotient again, right? You get quotient again. After you simplify, you get 2 natural log of x over x. I'm pretty sure this is going to be 0. Why? Because natural log of x grows much slower than any polynomial. Okay? But if you don't see the result, you can continue, right? It's also an infinity type. Therefore, you can continue to differentiate numerator and denominator. Natural log of x approaches infinity as x approaches infinity. So now you can 1 of x. And this is no longer a infinity over infinity type. And clearly, you know, the numerator is always 1. So the denominator approaches infinity. So the answer will be 0. So that is 0. All right. I think, I already knew the result, the answer at the very beginning. The reason is, here's my claim. Natural log of x over any x to any positive power, this is always equal to 0. So natural log of x grows slower than any power function with positive power. No matter how small the alpha. Alpha could be 1/2, could be, you know, could be 1/2, could be 0.0001. Doesn't matter. Okay, can you prove that direct? Well, clearly, this is the infinity over infinity type, right, at the very beginning. So you can apply the formula. L'Hopital law. It's alpha times alpha minus 1. Here's 1 of x. Okay. Alpha is positive. Then you simplify. You simplify, you move x to the denominator. So you get alpha, x to the alpha minus 1, so times x will be just x to the alpha. Okay, after you simplify. This requires, you know, some algebra skill, you know, you can quickly simplify. Okay. And after you finish this course, you practice, you will improve your algebra too. Okay. So that is going to be clearly, right? It's not an infinity over infinity type. the denominator is getting larger, larger, large, so the quotient is going to be 0. So the answer is 0. Because I know that, therefore, natural log of x squared over x, this can be written as natural of x over x to the 1/2 squared. So inside, it's already approaching 0 and square, you know. This is going to be 0 squared as x approaches infinity, right? So you can see that y is 0. Right? You can get the result in a different way. Natural of x over x to the positive power approaches 0. And of course, it's a square approaching 0. Right, so the next problem, when x approaches 1, and you have x sine x minus 1 and 2x squared minus x minus 1. So how do you find the limit of this? Yeah. So first of all, you check whether what type of this, right? When x approaches 1, you get sine 1 minus 1, so it's a 0. Then denominate, when you plug 1, 2 minus 1 minus 1, that's 0. 0 or 0 type. So you can differentiate. Yeah. Yeah. So yeah, then you get the derivative numerator, which is product. You get sine x minus 1 plus x cosine x minus 1. The denominator will be 4x minus 1. Then when you plug 1 for x, you get non-zero in the denominator. So you cannot apply L'Hopital's rule, just plug them into the formula direct. 4, 1, minus 1. And the sine 0 here, plus 1 times cosine 0. Right? And then you will get 1 and the 3. So it's 1/3. So it's getting easier, right? Just be careful, you know, every time you check whether this is 0 or 0 type or infinity type before you apply the L'Hopital's rule. All right, so we try next one. All right, let's find another problem here. Okay, so find the limit as x approaches infinity and the square root of x e to the x over 2. Okay, this is a product of two functions. I cannot apply L'Hopital's rule directly to this problem. If I'm able to express as a quotient, then I can try. Okay, so this is going to be limit as x approaching infinity, square of x e to the x over 2. So let's look at what type of a function here. As x approaches infinity, the numerator approaches infinity, denominator approaches infinity. So I can apply L'Hopital's rule. Okay. Yeah. When you do the problem on the quiz on test, make sure you put a note beside that before you differentiate the numerator and denominator. Okay. if you do like that, I know you're applying L'Hopital's rule. You don't even mention L'Hopital's rule, okay? Because it's clearly you're using L'Hopital's rule. Okay, so derivative of square x, I already know that it's going to be 1 over 2 times square x. So derivative e to the x, I know it's x over 2, and differentiate the numerator, differentiate the power, let's get 1/2. So we have to simplify carefully before we continue. Okay, so e to the x over 2, 2 times x square x times 1/2. So it's like that. Okay, 2 cancel out. So now it's clear that it's not going to be infinity over infinity type. It's not going to be 0 over 0 type. And the numerator is constant, denominator is getting larger and larger. And then clearly, this is going to be 1 over infinity. It's going to be 0. All right. So let's do problem number 46. Yeah, some of the problems are even number problems. And from the book, it's x approaches negative infinity, x natural log 1 minus 1 over x. Okay. Well, this is not a quotient again. So you have to bring one of them to the denominator, right? Create a quotient. And I think you can move x to the denominator. That's a pretty standard technique, right? It's going to be 1 over x. Okay. At this point, for the simplicity, you can use a substitution for the limits. I suggest you to use substitution. I don't like to differentiate. I don't want to differentiate 1 over x. Okay, I let u to be 1 over x. When x approaches negative infinity, okay, u approaches 0 from negative side, right? Why? 1 over x is always negative, and 1 over x approaches 0. So that means x approaches 0 from negative side. So I can change the limit. I can change to, this is going to be natural. 1 minus u over u. Right, so much simpler, right? Then I look at what type of this. It's clearly denominator 0, right? Approaches 0. The numerator, it approaches 1 minus 0. Natural log 1 minus 0. Natural log 1 is going to be 0. It's also 0 type. So there I can apply L'Hopital's rule. So denominator, the derivative is 1. The numerator is going to be 1 minus u. And then differentiate 1 minus u, it's going to be negative 1. Okay, so let me simplify a little bit. It's going to be, I have a negative sign. I can just let's switch the order, change the order. Okay, it's going to be 1 over u minus 1. So if u approaches 0, the denominator approaches negative 1. So clearly, it's going to be negative 1. Okay. So this is the answer. So the product can be changed to quotient. Okay. But how about the subtraction? Okay. Well, it's a subtraction. I can, L'Hopital's rule only applied to the limit of a quotient to functions. So this subtraction. Well, just combine them, trying to express as as a quotient, right? So how do you do that? I can e to the x minus 1, don't worry about that, you know. The numerator minus x, that's fine, that's quotient now. It's complicated, but it's quotient. Okay. Then I check, I plug 0 for x to see if it's going to be like a 0 over 0 type or infinity over infinity type. And clearly, the numerator is e to the 0 is 1, 1 minus 1 is 0, so it's a 0. And denominator clearly is 0 because there is a factor of x. So it's a 0 over 0 type. And apply L'Hopital's rule. It's a little bit complicated, but the idea is clear, right? So you can apply L'Hopital's rule. All right, so now differentiate the numerator. It's easy. E to the x minus 0 is minus 1. All right, the new denominator have to apply L'Hopital the product rule. So it's going to be derivative of x, it'll be e to the x minus 1 to 1, plus x, the derivative of e to the x minus 1 will be just e to the x. Okay. Then now most of the time, you can just find the limits right away, right? But this time, if you plug 0 for x in the numerator, you still get 0, right? And you plug 0 for x into the denominator, it's also 0. Okay, let's continue. It's a 0 over 0 type. I cannot find a limit directly. I have to continue. You cannot say the limit doesn't exist. 0 over 0 type is just the limited case. Okay? It's not like 0 divided by 0. If it's 0 divided by 0, it's already undefined. Okay? But this is the limited case. So let's continue. Find the derivative. So e to the x, and here is to the x, plus product rule e to the x plus times e to the x. Okay, that's the derivative. Okay, now when you plug 0 for x, and you get 1 over 1 plus 1 plus 0. So it's going to be, you know, you can simplify a little bit if you want to find a limit. I think when you simplify, it gets 1 plus 1 over 2 plus x, because e to the x all cancelled out. E to the x is gone. Okay, then it's just equal to 2 plus 0, which is 1 over 2. So we find the limit. So 1 over, yeah, this 2 has a limit. Right? Now, how about this? Every problem is new right here. This is going to be x over, right? I cannot combine them into one. In the quotient. But this natural log, yeah, I cannot combine them, right? It's not easy to do that. If you have to do, and you create another complicated function. Yeah, let's see. Try to combine them into one, then it's not going to be, you can try this. How do you get it? How do you put them together, right? Is there some natural log on the one side? I can do like that. X is going to be natural log e to the x, do you agree, right? Right? Then I can have two same log and I can put together. Okay, so it's going to be natural log e to the x of x. Great. So that's the kind of quotient here. Of course, that's only one single function, but inside the function, there's quotient. If the inside function, the quotient has a limit, then I can find the limit. Okay? Why? This should be equal to infinity since the limit, what is inside, is going to be infinity. Okay? This, if you differentiate, it's e to the x of 1, that's going to be infinity, okay? So that's why, yeah, that's why the limit should be natural log of infinity should be infinity. We still, yeah, somehow we still express as a quotient, but it's inside natural log. So now we discuss the product, how to change the product to the quotient, how to change the difference to the quotient. Right? Now, how about this? As x approaches 0 from positive side, whoa, x to the power x. It's defined, x is positive, so x to the x is defined. Now, this is not a power function. It is not an exponential function. Exponential function means a to the x. A is fixed. Power function will be x to the a. A is fixed, and the power is fixed. Now both the base and power are changing as x approaches 0. So you have to modify the function in order to solve the problem. Okay. So how do you modify? There are a couple ways to modify. You see, we have a formula, right? X equals natural log of e to the x, right? Another formula is x equals e to the natural log of x. Those are the two formulas. Very useful formula. We can use any of them. I think I should use the next one, the second, in this particular case. So I use the second one, it's going to be e to the natural log x to the x, right? Why I have to use second one? And if you use second one, then I can apply the formula. It's going to be e to the x natural log x. So it's not like x to the x now. It's x times natural log x, much better. So if we are able to find the limit of x times natural log x, then I can be able to find the limit. So all I have to do is find the limit as x approaches 0, x natural log x, right? If I know the limit of this, I can find the limit of the original function. Yes. Yeah, e to the natural log x is going to be x. I use this identity. You mean the top one?
Yeah, because like
if I use the top one, it's not working here. X equals natural log e to the x to the x. I cannot simplify.
You can pull the x down to the natural log, right?
No, I cannot.
Yeah.
I know this is useless here for the problem.
I know, but what you did is pull the x down to the natural log of x. That's what I was saying.
Yeah. So here I see.
Yeah,
this is put to here. That's what this came from. Okay. If I use a second identity, I can able to do that. But I use here, I cannot modify this. Yeah. Okay. I cannot modify it. X to the x is still there. This part I cannot separate. There's no formula I can use. Right? So this does not work. Only the second formula works. Okay. I can change x to the x to the product. Okay. Product is much easier to handle. I will. Okay. So when x approaches 0, now I still have to change it to this form. Okay. Right. But this is going to be infinite over infinite type. I can use a L'Hopital's rule. Why infinite over infinite type? Natural log approaches negative infinity. 1 of x approaches positive infinity. Okay, as x approaches 0 from positive side. So it's infinite over infinite type. So I can apply L'Hopital's rule to solve the problem. it's going to be 1 over x. This is 1 over x squared. Right. But after you simplify, you get a negative x. Then it's clearly the limit is 0, right? So now x times negative log of x approaches 0. So you can simply write here approaches 0, which is 1, as x approaches 0, right? And you can say see the work below. Yes.
So I'm just confused. How did you get rid of the e there when you moved x in front of the log?
I did not get rid of the.
Like, I was just confused. How,
He just saved it for later because it's not used yet. So you put it to the side.
Yeah, I put it aside.
oh, so you're doing another limit to figure out the first one.
Yeah, I did not get rid of e. I just say let's figure out this limit. Right? I don't want to keep writing e there. So I consider this. I look at this limit. I apply the L'Hopital's rule to this, and I get the limit to 0. Then I go back. I say, hey, this is the power of the e equal to 0. So this. So this is a part support this conclusion. All right, so let's take a look at this problem. X approaching infinity, 1 plus 1 of x to the x. All right, this is also an interesting limit. I think 1 plus 1 of x is getting close to 1, but the power is getting larger. Does it have a limit? This is if you find a limit, you can find the limit of this, right? It's the same. It's guaranteed that one has a limit. And here takes integer value. And this x is the arbitrary value, right? So we know that this is going to be e, right? But it's a definition of the number, actually. Yeah, so, but suppose we don't know this part, okay? How do you find this limit? I already know the answer. The answer should be e. The limit is e. Because I remember this one of the formula for the e. How do you define the e, right? There are many ways to define the e. And this is a definition of the e. The number e is the limit of that sequence of number. Okay? Yeah, there are several ways to define the e, okay? Yeah, you have to define the e first. Or, yeah, there are multiple ways to introduce a number. Okay, there's only unique way to introduce a number pi. Okay, pi basically is this half of the circumference of unit circle, or the area of the unit circle. Okay, because pi r1 squared. But the e, yeah, this is one of the definition for the number e. And all right, so let's try to find the limit. Okay, the limit is going to be e. I knew it. Okay, so this is not the infinite over infinite type. It's not in quotient form. So what I'm going to do? So 1 plus 1 of x to the x, the same. Use the same technique. It's e to the natural log 1 plus 1 of x to the power x. Okay. Because of that, you can write as, all you have to do is to find the limit of this part. Okay, what is that limit? Okay, this is not still not in the quotient form. Okay, so I'm going to, I did not get rid of E. I just say, let's start over a new line. I just consider this power. And then this product can be easily changed to the quotient. That's a standard way to do that, right? Then let's see what type of this. I think this is 0 over 0 type because x approaches infinity, right? As x approaches infinity, the numerator approaches natural log of 1, which is 0. Denominator approaches 0. It's 0 over 0 type. Now you can change the variable if you want. 1 of x, a little bit, change it to the another variable, then another variable approaches 0. But you can leave it like that. So you can apply L'Hopital's rule, okay, to find the limit. Okay, so let's find the limit as x approaches infinity. Differentiate the numerator. Okay, the differentiate the numerator will be 1 plus 1 of x. Then you have to differentiate 1 of x, which is negative 1 of x squared, right? The denominator is negative 1 of x squared. So that cancels out. You will get, and then clearly this is going to be 1. Yeah, this is going to be 1. So you plug a 1, go back to the original, expression, right? 1 plus 1 of x to the power x is e to the natural log, right? So now you know this is going to be, the limit is going to be 1 as x approaches infinity. So the answer is E. Right? So E is a very interesting number. Nobody knows, if you express it as a decimal, in a decimal form, you can have 1,000 digits. Nobody can write down all the digits. There's no logic. Okay. Yeah. It is really a very special number. Okay. Identified by human being. I should say that. We call it E. There's 2 important numbers in the world, pi and the E. Okay. Pi is irrational number, could be understood by many kids in the middle school, elementary school, even, right? Of course, it will not be understood by Congress. Okay, just kidding. I told you, there was a story, Indiana congressman in 1950s or 60s, they're trying to pass the bill. In Indiana, we define pi to be 3.14, otherwise too complicated. We don't want this very complicated number. That was a joke, but indeed they did. And many politicians that don't know addition multiplication. You know that, right? So it's not surprised. Okay. Very few politicians are really good in mathematics. Except for there was one politician in France, I think he got the fields medal. He decided not going to stay in academic. So he's in the government. All right, let's do the problem. Next problem. Yeah, why I said that politicians that don't know mathematics, because simple subtraction, because when they claim I'm going to give a tax cut, but then when you cut too many, you get negative, right? The budget. So you have to tell the people, how do you create, make them, create the money, right? There should be addition minus, so you can keep it balanced. Otherwise, we're running into the deficit, right? And the deficit, that the United States deficit can huge, huge, double. Every 8 years, double. That's the limit is horrible. You know, we're talking about limit right now, right? The limit. I hope someone can modify the function of the limit. Okay, so let's do one more problem. Okay, this is a x. All right, so let's do this problem. Okay, this is slightly different, right? X approaches. All right, let's figure it out. So this is strange. I don't know what is limit at this moment. Okay, I did this problem last year, you know, but I forgot the answer. I can memorize all. Okay. So let's see. We can modify it, right? The idea is we modify this because it's not a quotient, right? It's 1 of x. That's a standard technique. E to the natural log x 1 of x, right? So you get this. So now it's okay. The power of E is just a very nice function. It's in the quotient form. Okay, you can you know, if you don't want to start a new line, you can work on like this. You change you can keep writing on this, right? So e to the natural log x approaches infinity, and natural log x over x. You can write it like this. Okay, this is a number. But now it's zero, infinity over infinity type for the limit. So you always put that x approaches 0, and here's 1 of x and the 1. And clearly the limit is going to be 0. So it's going to be 1, not e. Right? So the limit is 1. It's not e. Right? So here's problem number 68. Two x minus 3, 2x plus 5, and 2x plus 1. Wow. This is a problem. How do we figure out the limit? I don't want to modify the function too much because that's not a very general idea. And so what I'm going to do is I use the above technique, 2 to the x minus 3 over 2 to the x plus 5, because both the base and the power changes. So that's you have to use the e to the natural log, right? And 2 to the x minus 3, 2 to the x plus, 2x plus 5. And you have the power here. You can move the power down to here, 2x plus 1. Then we still have a problem, right? How do you find the limit of this new the power? I think we can do that. Okay, so I can see the natural log 2x minus 3, 2x plus 5, and then here's 1 over 2x plus 1. Well, this is a really complicated limit. So what type of limits we have to figure out? When x approaches infinity, the numerator approaches natural log of 2 over 2. So it's natural log 2 over 2. And that is going to be 0. Okay, it's infinity, positive infinity. Okay. Yeah, it's from positives. Just natural log, no, it's a 0. So it's a 0. So natural log 1 is going to be 0. The denominator also approaches 0 because because the numerator as it's 1 over 2x plus 1. So it's a 0 over 0 type. You can apply the L'Hopital's rule to find the limit. Okay, looks like a complicated, but we can find the limit. Now, how do you differentiate the numerator? You have to express the numerator in this form: 2x minus 3 minus natural 2x plus 5, and here's 1 over 2x plus 1. Okay. All right. So now let's differentiate. Okay, it's 1 over 2x minus 3 minus here 1 over 2x plus 5. And this will be 2x plus 1 square. It's 2. Okay. You can differentiate. Yes. All right. So now, what is next step? We have to simplify. Otherwise, we are not able to find the limit, right? Simplify, this will be 2x minus 3, 2x plus 5, and 2x plus 5 minus 2x minus 3, I think it's 8. Let me quickly finish that. Okay, then you have, okay, then turn upside down. Again, negative 8 divided by 2 is 4. Then I have a 2x plus 1 square, 2x minus 3, 2x plus 5. I think I'm going to get a finite limit. The numerator, all right, is 2x plus 1. So the leading term is 2x. So you get 4x squared. All right. So here 4x, so the quotient actually is 1 approach. But should you differentiate again? It's an infinite over infinite type again. I don't want to differentiate. It's math. Okay, too complicated. So what I'm going to do, I'll use the traditional method. I take 2x out. So I get 4x squared, 1 plus 1 over 2x squared, right? I also take 2x out from each. So I get 4x squared, 1 minus 3 over 2x, 1 plus 5 over 2x. Then those two cancel out. Then it's clear that when x approaches infinity, you get 1 plus 0 square, 1 minus 0, 1 plus 0. So the answer would be -4. Okay. That would be easier. Otherwise, you see, how do you differentiate numerator? How do you differentiate denominator? I think it's getting more complicated. Of course, eventually you can simplify. So it's better to just take 2x out of each term, then use a traditional method to solve. It's not always use the L'Hopital's rule. Okay. That's it. So we stop here, and next Monday double check if you guys are free or not.